No, sir, you're not audible.
What about now? No?
Yes, sir, it is audible.
Now you're audible, sir.
Okay. I don't know sometimes. Okay, so I will we will go to the last topic of which we were discussing. Of course, we were trying to solve some problems in this direction in the tutorial, but I will just formally cover it. Nothing great about it. So the point is, once you have a full closed loop transfer function that connects input to output, or rather set points to the output or disturbance to the output, which call it as servo and regulatory programs respectively. Okay. So eventually you would like to know whether whatever embellishments that you have done, okay, is making things good or worse. For instance,
Voice is breaking in between.
how about now? I don't know, yeah.
So the screen is not shared.
Oh, I'm sorry. That is my mistake. It should be possible now, guys.
Yes.
So now it's
Some lag. Yeah, some lag. So institute internet seems to be little wavering today. Okay. So I hope my voice is also better, guys. Isn't it?
Yes.
So what I was trying to say is the following. So once you have your transfer function ready, that is what we were trying to model. For instance, input as a function, output as a function of two things. One is set point, which is the classic servo problem, and the disturbance, which is the regulator problem. So once you have done, so we have added measurements, controller, valve, process, maybe whatsoever additionally I2P, everything. You will have to look for whether this added add-ons, I would like to call. So these add-ons are making things good or worse. So that just check. The only way to look at it by looking at stability. So we have looked at, as I told, there are various definitions of stability, but we will look at the most simple one. Bounded input, bounded out. If you send in input that is bounded, that is, which means that's something that is not infinite, infinitely growing, or that is not infinite. Your output should also be bounded, which means that should not grow beyond the designed, or rather expected limits. So this is essentially look at the denominator transfer function. So denominator polynomial, which is also known as a characteristic equation. Why? Because if you take the inverse of it, okay, if the inverse, the root would come in play a role. Okay, so if you write them as partial fraction and calculate the root, you would say this p s minus p1, so on and so forth, and you would see integral p would come. Unless the p is not negative, this is a growing function. If p is negative, it is a decaying function. So you will have to look at whether p is negative or what. So rather p1 to pn is negative or what, because if it is positive, it's an exponential function, it will always grow. But if it is negative, we have always seen first order like characteristic, which is a decaying characteristics. To
Hello,
check
sir.
that, yeah.
Sir, why all these p need to be like negative? If even one is positive and others are negative, couldn't it be a bounded function?
No, it will not be. Na? So one would keep on growing, right?
But maybe other terms can make it bounded.
Will not be, because one is always growing to infinity. Na? whatever, so something is going fully to infinity, whatever you do, and something you are trying to push down, how much you will be able to push down. Asymptotically, the one that is going to infinity will be winning, right? Because there is no
Yes,
end, there is no end to it, no? So it's a good question. So the necessary and sufficient condition is to have all these roots to be positive. Sorry, all these roots to be negative, so which is lying in this side, which is the stable region. And this is the unstable region that would make almost things would worse. Okay, so now how to check it? We know it is the roots. Okay, you have we have already done it for first order system and second order system. It's basically the denominator roots. Okay, so so how you have to basically check they are lying in this. Let me mark if I have a green color here. Yes, this is our what you call good area, which is left hand side, which is generally, so there are various connotations. They will call it as LHS of the LHS plane. So which means that it is basically lying left hand side to the what you call the origin. And I'll also have a red one. So this is our danger regime. So this would always make it unstable. So it's very simple. So there is nothing complex. So again, people will call it as RHS of the origin. So intuitively, it is a very clean thing. We know it, but only thing it is the checking become difficult. So just to add some of the things, if it is, let's say, even the root is, so this also we have seen, if the root is lying onto the axis, you would see that it would be a stable response like our first order systems. Sometimes you would see that you would have a positive and negative, not positive or negative, complex conjugates. This is more like a second order system. It would always converge though, but you would see some oscillation due to the this competing guys, but eventually converge. But on the right hand side, this is fully off. So if something is lying here, it is unbounded, and something is lying as complex conjugate, it would be oscillatory unbounded. This would keep on increasing and going outside. So this is all we know, but only thing, the problem is how to check this. Because second order system, good, you can calculate the roots. First order system, very easy to calculate the poles. But let's say if you have nth order polynomial, it's slightly difficult to do. So this Ruth, so Ruth and Jury, they were the two people kind of figured out, found that this is definitely not a problem of control system. This is a problem of finding root of a polynomial. Correct? So your denominator transfer function happened to be a polynomial. So we are checking the root. So you are saying this is nothing, they have told that this is nothing very clear to. This has no specific bearing on any process control or even control theory. It's a problem in mathematics where the roots of a nth order polynomial are located. So Ruth solve this problem in continuous domain. Jury solve this problem in discrete domain. So there is, so since transfer function is continuous domain, we will learn it as Routh stability criteria. And I have not told, you might learn this maybe if you take an advanced process control, and if you have the book that you have, and if you browse some pages ahead, you see that there is something called Z transform, or you might have even learned about it. So Z transform is the discrete equivalent of S Laplace transform. If you are working in discrete time domain, and which means that, so here is all PDE, ODE. In fact, ODE, there it would be difference equations, ordinary difference equations. So then the steps that you need to do is apply something known as Z transform. So Z transform would also give you transfer function, but in the domain of Z, because it is discrete in nature. So again, so I don't want to deviate. What I'm trying to say is Jury solved this problem in Z domain. Roth solved this problem in S domain. So eventually they are same. It is finding out the roots and placing them. Okay. So what Ruth told, are the following. So you have to look at the coefficients of this polynomial. If at least one root of the characteristic equation lies to the right or on the imaginary right, the system is unstable. We know. So he is saying any coefficient is negative or 0, then at least one of the root of the characteristic equation is lying right. So you have to look at the sign of this coefficient. It has to be if at least one is negative or 0, so then you stop. Then eventually that itself makes things unstable. But all of them are positive. Let's say this an minus 1, an to a naught are all positive. You have to do, okay, so it's like passing one step of the test. Okay, so then either this candidate doesn't seem to be unstable at prima facie from the first look, but you will have to do further test. It's like RT-PCR 2 test. No, you would have a confirmatory test. Okay, then there is a initial test, then there is a confirmatory test. So if the initial test itself you are negative, they don't do the confirmatory part in the RT-PCR, you see. And then initial part you see some level of protein, then they would do the second part, which is the confirmatory part. And if that is negative, you are negative for COVID-19. If that is positive, you are positive in COVID-19. So this is like this. So in the first step itself, if these guys are negative, you are out. It's unstable. But say all of them are positive, you do one more check. That check is making something known as Routh array. Routh array is nothing but a nicely made table. How to make it? So let's say if there are n coefficients. So the point is, if you have n coefficients, you have to make a table having n plus 1 row. Okay, and there is an algorithmic, not even algorithmic procedure. It's a very simple. It's a manipulation that you would do. So you have to write the what you call the coefficients like this: an minus 1, an minus 1, an minus 2, an minus 3. So an minus 1, an minus 1, an minus 2, an minus 2, an minus 3, an minus 4, an minus 5, until all your coefficients are exhausted. So this is given. So first two rows would be always given to you, because you would have, this is just copy paste from your polynomial. Then you synthesize the remaining elements. So how to calculate B1? Again, very simple. Okay, an minus 1 into n minus 2 time minus an minus 3 divided by an minus 1. Similarly, how to calculate B2? Okay. So you have to make sure that it is pivoted with respect to the first column. So everywhere, so you would calculate the second element B2 like an minus 2 1, an minus 4, sorry, an minus an minus 1, an minus 4, an minus 5 divided by an minus 1. So your first column is you will always use. Then you use the same procedure. You build upon. So once you got B1, B2, then you can calculate. So if the order of the polynomial is 3, so if n is equal to 3, you have to construct until there are 4 rows. So C1 in that correction, which is the next row. So how do you calculate C1? Okay, B1 into n minus 3, n minus 1 into B2 divided by B1, so on and so forth. And the check that you need to just do is you have to always make sure that all the first column, all elements of the leftmost column, which is the first column, has to be positive. So then you can say that these guys are stable. So this is more useful when you have polynomial n greater than or equal to 3, because n is equal to 2 is easy. N is equal to 3 means that you will have to factorize, and you might tend to make mistakes, or if you have to numerically solve, it's cumbersome affair. Otherwise, you just need to do this. Any doubt on this?
Yes, in the previous slide, I think we said that if any of the coefficient is negative or 0, then the root might lie on the imaginary axis, and this would make the system unstable. So, sir, if the root is lying on the imaginary axis, why would the system be unstable?
No, it is generally not unstable. Unstable is slightly so no. Okay, so what I am trying to say is, it is the right to the right on the imaginary axis. It could lie to the right or onto the imaginary axis. Okay, so you read it that way. So all right is always unstable, huh? Okay, correct.
Yes.
So here this is basically known as critically stable. Correct. So which is essentially means that this is the boundary condition. You see, this is critically stable. So you would eventually try to call things lying exactly on the imaginary axis as unstable. Why? Because you don't have any guarantee or any margin, because these are all numerical numbers, right? So if you calculate, so let's say s is equal to 0, huh? Which is something, this is what this x, rather this is corresponding to something equal to 0, right? And if this number is, let's say, 0.000000001, it is technically non-zero. Whenever you do numerical calculation, it would tend to make it 0. Got it?
Yes, sir.
So which essentially means that you don't want to take that risk, safety margin, because it's always lying on the axis. It's critically stable. So if you touch it, it becomes unstable. So we would tend to consider them as unsafe case. Is that making sense, Shruta?
Yes, sir. It's clear now.
Okay. It is like when the pendulum is at the which position? It's like inverted pendulum is lying on the top. If you touch it, gone. It's like as delicate. So we would always tend to avoid that case. So right is of course gone. Left is very, very critical. So that's all. Any other questions here? Okay, so I have solved one or two problems related to that in the tutorial. I'm not going to take this. You can check this. This is like as simple as that. You are asked, so the problem is here to check what value of Kc that makes this thing stable. Okay, so this is third order polynomial, difficult to factorize. You make the root array. How to make it? 10, 17, 8, 1 plus Kc. Then you calculate B1 and B2 as it is. And what is the condition you need to put in? The calculated value of B1 and C1 should be greater than 0. You put the condition, so you need to get the value of Kc that makes the system stable. Okay, so now there is something known as, it's just more of an introduction, okay. So there is also, so eventually you need to know the stability of the system for an unknown variable in the case. So for instance, if your transfer function containing a controller term and you need to fix that controller Kc sometimes, and this Kc should make your system stable. So of course root array gives you that range, but if you need to look at the profile, this is more. Okay, so I would like to make, so this is more of an analytical approach, which essentially means that it is numerical. It would give you analytical solution of whether stability or instability, and somebody would like to look at graphically how this thing happens. Then you will be able to look at, you will be able to draw something known as the root locus diagram. So root locus diagram is just like, is nothing but how the root of the characteristic equation, it's the profile of the roots of the characteristic equation, which is essentially the pole, how change if you have how it kind of vary with respect to if there is a parameter in the equation. So look at this. So this, you wanted to see here, what you really need to know, whether how this Kc affects the stability. So again, so this is GOL. So your denominator term is G by 1 plus GOL. So you have, so what you have to write first is 4 Kc by S1 times S2 times this thing plus 1, okay, and write the pole or the characteristic equation, which is this. Now what you are in this root locus diagrams, okay, what you are going to look, you are going to plot the roots of this equation with respect to the changing values of k. Okay, so first of all, k is 0. So that's a very definitive answer. You would get s1 is equal to minus 1, s is equal to minus 1, minus 2, and minus 3. Minus 1, minus 2, and minus 3. This is the case when k is equal to 0, which essentially means that the system is stable. Now you start increasing the kc. Okay, so you have to do it numerically, slightly difficult, and softwares would help you to plot it. Hand would be possible, but you'll have to, if it is a higher order polynomial, maybe slightly difficult. For a first order polynomial, you will, or second order polynomial, you will be able to do it on your own. This is a third order polynomial, slightly difficult. When kc is equal to 1, kc is equal to 1, essentially it would essentially means that, okay, it would be a complex conjugate. So this is drawn. So when kc is equal to 1, there would be one root over here, there would be another root over here, still in the what you call positive side. So now what happens if kc is increasing? This root profile tends to grow like this. And so there are three roots. One is going in this direction also. One is moving towards the negative side, and two is going towards positive side. Okay. And after some critical value, so let's say k is equal to 15 in this case, this root profile cross the LHS, which is our green area, and going to the RHS, which is the danger area. So you would be able to check at this point, okay, things become overwhelmed and things might go unstable. So this, if you need to get graphically, so this gives you more idea. So what is the idea that you are going to get? Okay, since this has become a profile, if I were defining a control system, I can say anything beyond this is a very safe region. And if you put a factor of safety, why factor of safety, as Vishruda asked? So something very close to origin is always danger because of some numerical numbers. These all calculation. 0.0001 can also act adversely. So if you put a factor of safety somewhere here, let me put with some color. Okay. So what I am trying to say with this factor of safety, okay, I don't want to go beyond this. This is like what? Assume this as a black hole, and this is something, this is your event horizon. I know what, I hope you know what is that. Anything beyond the event horizon would be sucked inside the black hole. So similarly, if I put an event horizon here, which is like the safest thing, it's like a cage wherein you go to a zoo where you keep all carnivorous animals, zoo like lion or wherever. So you don't want to go close to that. So you would put a cage, and this is that cage. So I'm sure if you go inside this bag, so once you have this root locus diagram, so how do you draw it? Only way is put this number, solve the problem, and do it. So there is no simple way to do it, but it would give you an idea. This is my operating premise. I don't want to go closer to the place where I become in danger, but so I would get a space wherein I can play around. So this is help you to get that kind of a information. So it is basically the loci of the roots of the what you call the denominator polynomial. Okay. Any questions here? But how to draw it? There is no way out. You will have to solve the problem for different value of kc, calculate the root with some intervals, and check how it profiles. It's like drawing a graph, nothing else. But the insight that is providing is more clear. Here you are only providing more. Here if you are providing more analytical insight, this is providing you more of a graphical insight. So when you are designing a control system, you might even do both. Okay, so that this may be for your reference and this may be for your calculation, so on and so forth. And you might even check whether they are concordant, so that, because see, when you are fixing a distillation column and designing a controller, you cannot or forget about that. Let's say you are doing a self-driving car development, okay, and you are trying to define what you call the how the cruise control to be made. So again, you need to have a controller, no? Otherwise, how do the cruise control works? So cruise control is basically it's a type of controller. You fix a set point of the speed, and it drives in that thing. Okay, you don't want to make your car crash because then all the reputation of your company goes away. So people would tend to do multiple such analysis and comes up with a safe range because it has to be significantly robust so that things will not go bad. Any issues at the moment, guys? Otherwise, we will do the next step. All clear? Hopefully.
Yes, sir.
Perfect. So now we will start taking up a related topic. Give me a minute. Okay, so till now what have we done? So just again put things perspective so that you won't lost. Okay, so what have we done? So we have now looked at the closed loop transfer function. Okay, sorry. So we have looked at the closed loop transfer function. We also have looked at how the stability, how it works, because you don't want to crash anything technically. So you can do various ways. Basically, it is the poles of, oh my goodness, this is insane. Cool. Where no, yeah, here it is. Okay, basically it is the poles location. Okay. Okay, so basically, okay, so I'll also tell you some additional information. So now what are you doing? You are looking at the poles and checking whether it is stable or unstable. So you can also design a pole by some means, for instance, tipping the controller structure, so on and so forth, so that your poles are lying exactly on the LHS regime. So that problem is known as pole placement. It is the reverse problem. Well, what are, so you will figure out your, or rather you design their controller in such a way that its poles are always placed. Poles of the closed loop transfer function are always placed within the LHS. So that problem is known as classic pole placement problem. We are not going to do that, but what we are trying to learn is, okay, so assuming that, so basically we are doing analysis, we are not doing the reverse engineering. So you can basically, if you find the existing values and when you do the analysis and you find the roots of 1 plus GOLS and we found it is S is greater than 0. So you can also tweak, how to tweak, you change the controller parameters, add some positive, negative here and there, and you place the pole back to the LHS. So that problem is known as pole placement problem. I think just for your information, somebody who would be interested to perceive it further, we are not going to do that, or rather learn that. But what we are going to do now, so now we have kept everything. So your GOL by 1 plus GOL, which is the overall transfer function you have, which is the closed loop transfer function. It's one of the component is GC, which is the controller. So now let us, so what have we learned till now? We know that there are three type of classical controller. Okay, and when we can also put all the elements that needed for the controller to make a closed loop transfer function, and we can check, or rather do an analysis whether it is stable or what. So now let us learn, can we tune this DC guide, which is the controller, so that we will get the desired performance. So there are two things. One is stability, one is performance. So what is stability? Stability is more of not crashing the car. But if you look at the example, here stability means that you don't want to crash anything. That does not mean that you are having a bumpy ride in the car. Correct? So you made your self-driving car, okay? Look at its closed loop transfer function, and it is all negative. Okay, so you say that it's super, it's not going to crash. Okay, so but when you start inside, when you are start riding on it, you found that this car tend to kind of having a very bumpy ride. It's kind of shivers, or it kind of not driving properly, bumpy ride technically speaking. So this kind of problems comes in what is known as performance. So eventually any control system or anything that you design for automation purpose, be it self-driving car, be it chemical process control, be it robotics, should have two conflicting characteristics. One is stability, which means that things are not crashing. And the second is performance, which essentially means that you should have a smooth ride. So which essentially means that your distillation column is giving you very nice output at a very good what you call purity level without any disturbance. Performance is good. So again, so stability, you are riding in an aircraft, it is not crashing, it's perfectly stable, but it tend to do a lot of mischief in the air, it tend to shiver. So you would feel like, what is this? So anything that you design in automation should be a combination of 1 plus 2. So we have now learned the one aspect of it, which essentially means the stability by looking at the poles. Now let us look at the second aspect of it, which is the performance, which essentially means that you would get a smooth response. Eventually, their harmony is what makes your product success. Okay, so now okay, now coming to the performance. So how do you do the performance tuning? Only parameter that you can tune in a control system is your controller settings. Why? Okay, look at the things that you have. One is process, untouchable, right? Processes, you have been called to control the process. It is made by someone. You don't have any access to it. Okay. So second one is measurement. Okay, so you bought the sensor. How are you buying? You are buying from a vendor. No control. You have to just buy it. Otherwise, you will have to make the sensor on your own. Impossible. Okay. I to P. Again, you are buying it from someone else. No control. You are just adding to the system. Okay. What else did I miss? Okay. Control valve. You are also buying it. No, nothing. So control valve, or let me call it as final control element. You are buying it from the vendor. It has only spec. Okay. The fifth thing that you are also buying from the vendor, which is the controller, but the vendor has put a provision in the controller to change your KC, tau y, and tau d. This is technically the tunable parameter. So you can put KC, tau and tau d, whatever you want to tune, or whatever. If you are buying, or if you are designing a controller, you are forget about that you are buying it, you are designing it. You can tune this. So even though all these things, so 1 to 5 are all affecting the performance, your handle, basically your intervention you would do maximally on the controller side, because that is what you would be able to play around. So now maybe in next 2-3 class, what we are going to do is, how do we enhance the performance? Is this premises clear, or do you want anything more? Anything that is unclear?
No, sir, it's clear.
Cool, guys. So let's look at, so the chapter is talking about controller. Oh my goodness. I would like to make, just a second.
Hello, sir.
Go ahead. Go ahead.
So the stability and performance, these two terms are used interchangeably, or these
No.
two are
It is they are two independent business. Stability has to do with, as I told, not crashing. Got it, no? While performance is still it's all about improving the it's like having good characteristics. It is not interchangeably used. It has to be stability and performance, not or. Is that clear?
Okay, sir.
So as I told, this is the same example. Now, if you are riding in an aircraft, the stability of the aircraft remains whether it would crash or not crash. While the performance is okay, whether you are you are traveling it from Delhi to Mumbai, you say that, oh, I had a very smooth flight. So both of the performance would come in there. Let me check whether it has come in here. It might, yes, I think it is better to open it from here. Super. Eventually, it is a mix that gives you the overall performance. Huh? Not overall, overall behavior. No, again, don't use the word performance. Okay, so now we would say how to tune or design. Design in the sense, design and tuning, I will consider them as a single word, like how to give you better, good result. So why what we are saying is, okay, so this is a very simple example. If you have your, so this is the model. So consider a first order plus time delay model having k is equal to 1, theta which is your time delay minus 4 and tau 20. So 20 s plus 1. So this is your model. And you put a PID controller to it. I think it is PI controller to it, okay? And you see the various responses with respect to this characteristics Kc and tau I. So Kc is equal to 5, tau I is equal to 5, oscillatory, in fact unstable. Okay, Kc is equal to 5, tau I is equal to 11. Okay, again stable but bumpy ride. Performance is not really nice. Correct. So Kc is equal to 5, tau is equal to 20, slightly oscillatory, but still not great performance. Here it is stable but bumpy ride. So now if you look at this middleman, so it is stable, but there is some jump which is inevitable to any of this. Afterwards, this guy, it's like when you start your vehicle, it just did a jump, then everything was smooth. So, but here if you see, this is again slightly over changing with respect to time, so on and so forth. What I am trying to say is the controller parameter can gives you the both extremes. So this is not stable. While the others are all stable, their performance are not really nice. So you can tune your Kc and tau I. So these are all by means of trial and error. Because you put something and this is what you go. But can we do more better job here? Better job in the sense that can we design it? Like can we give this number as a solution of something so that it is more reliable and more accurate and gives you stability as well as performance. So that is the question and that is what we are going to address. Any questions at the moment?
Sir, which one of them has the highest performance?
So see, it's all about the definition, okay? So definition of the performance. So I would not call these or so you look. So this is not good performance because it has continuous oscillation. This is not good performance. It's a continuous oscillation. This is not a good performance, but it has because it has a larger shoot up. Then there is a jump. Then there is good in the sense these are all acceptable because not they are all stable, but not really good performance. Here you see this is also taking a lot of time. See, 100 minutes to stabilize. Okay, so I would say this center guy seems to be a best bet, but you may be able to do a better job if you do this things more scientifically. Because now what you have done, one of you went and started tweaking this parameter. Okay, I am going to put 5 and 5. What is happening? I am going to put the second person of you told, okay, since you are putting 5, 5, I am going to put 5, 11. Got it. Now this is more of a trial and error design. So here you see the performance, it is of course jumping up, which is inevitable, but you see by maybe 25-30 that bump got over. While if you see this is going up and taking a turn, it's again more than 50 it takes that. So eventually it should be some like this. No? So what I am trying to say is the stability has a very clear definition, while performance is a definition that is created by you based on the market needs. Fine.
Yes, sir.
Because let's say if you are again, automobile is the best example. Huh? So a vehicle that gives you performance, good performance on in a highway might not give a good performance in a desert drive. Because it is not intended to do that, or there are combinations that helps you to do. For instance, all this Land Cruisers or Prado, those kind of vehicles, it's good. It is used to drive both in the off-road terrains and the this what you call on normal highways. So performance is something that you define some and with respect to the market. But stability is more of a fundamental definition. So even if it is your what you call Maruti 800 or what you call Toyota Land Cruiser, it should not crash. That definition is very clear. Other one has a lot of other intricacies because performance is always dependent upon economics. Why? Because if you are ready to shed out more money, the more improved performance you might get. So basic characteristics, of course, stability, that you cannot compromise. If it is a car, if it is a distillation column, it cannot crash. Okay, so now coming out of the coming to the outcome. So maybe you would also, Bayer may also sell some product, maybe some company in Gujarat, Ankleshwar might also sell some product. So so I'm saying some chemical product which is coming out of distillation column. Maybe Bayer, which is the most one of the Bayer chemicals are very expensive. They might have fine-tuned in the process such a way that you might give you 99.99 whatsoever quality variable, while the one that is operating in batch in some, I'm not saying, I'm not of course not blaming them because that's the way they make their margin. Okay, it might be only 99% or maybe 98%, but for buyer you might shed out $1,000, but for this guy you might only pay even $400. So this is like a very complex phenomenon. So here is what the third guy of vertical automation comes into the picture, the optimization, which again we have not learned and you would learn if you would like to. So eventually you optimize performance and stability and economics. So things that is really what you call or rather if you want to do it in a large scale basis, you are basically optimizing, maybe I'll write it, stability which you cannot compromise, okay, performance or quality, I'll say quality, whichever you would like to. The third is cost, economics. So eventually these three you should be optimized together by means of any optimization method. So that is why we should all learn optimization to the core if you want to really do. So again, if I am talking about this a very generic example, there's no condition, it is not contingent upon our chemical process plan. It could be manufacturing, anything. For instance, it could be aircraft, okay, stability of the aircraft and performance of the aircraft and cost of the aircraft. So how aircraft companies are buying? So many of them would buy Boeing 787 for international routes. Some of them would buy Airbus 330 for international route. It basically in terms of the stability, you maybe so a 787 had some incident of battery failures in the earlier days. So stability little lesser, you would put some ranking. Performance, this seems to be the most fuel efficient one. Cost, maybe 87 or 30, 330 would have some different cost. So you would have to eventually optimize and buy something. Same applicable to if you are doing if you are operating in a chemical plant or so on and so forth. Is that okay?
Yes, sir.
Okay, so first criteria is stability. So if you are using performance criterion, the stability you cannot compromise. It is AND. So rest all can be OR, but this can be AND. And effect of the disturbance should be minimized. Something like this. Disturbance should be minimized. Here everywhere the disturbance is minimizing, but and rapid smooth response to the changes. It should be rapid and smooth. See, this seems to be the, so there is a bumpy ride initially, but later it becomes smooth, but others are not. So I am saying it's up to you to define the product, because that is what you intended to sell as the USP in the market. Steady state error should be minimized. Excessive control action. So this is a very important thing, excessive control action. Why? Because see, whatever control action you do, so let's say it's a reactor, and this feed stream is you are controlling by means of a control valve, and there is a controller here, GC, and you have a sensor here, some transmitter measurement. When you take excessive control action, the thing, who is implementing the control action in the plant? The poor control valve. Okay, so let's say, so this is the heat input and you are controlling the temperature. This is the jacket, and this is like a batch reactor, and you are controlling the temperature, measuring the temperature Tm. Okay, then it goes to temperature controller, and temperature controller is manipulating this control valve like this, and somewhere you have I to P. And what would happen if your controller is doing excessive control action? What do you mean by excessive control action? It is either continuously operating, it is continuously giving control actions which are extreme in nature. What would happen then? Okay, if there is a small temperature change, you wanted to make 80 degrees centigrade, and it has become 80.1. Okay, your controller is now saying, oh my goodness, everything has collapsed. Do something. So your controller is saying, okay, nothing can be done. Okay, make the valve full open so that the temperature is down. Suddenly it becomes 79.9. Okay, then controller again sending signal, oh my goodness, everything has collapsed. Do the full closure. So what would happen? It became a very excessive and coercive atmosphere to whom? To this poor person, which is the control valve. So the final control element will have to bear lot of unwanted disturbance which is coming from the control. As a result, this is one of the most expensive instrument that you would buy. The control valve, when you come to your process control valve, we can show you. This is one of the most expensive instruments. Why? Because it has moving parts. None of these equipments, controller or anything, would not have moving parts. So here this guy has a moving part, which means that generally that's one of the clean principles of manufacturing, right? Any equipment that has moving parts would have high maintenance cost, and it would also be expensive. So the control valve tend to have large scale maintenance schedule, which essentially means that you would change this guy in every 1 month, and eventually that happened to be not economical. Okay, again, so that become one criteria. Okay. Okay, so now maybe I will quickly, I think I have 7 minutes. I will, I can talk a little bit on what is known as how to design the controller to achieve one of the performance, like basically how to tune the controller. So one One very well established way is something known as direct synthesis. As it means it is very direct. That's why somebody has put a very nice name. Okay, so direct synthesis approach is based on you need a process model and you require a desired transfer function. I will come to that. But what is the problem with direct synthesis? Direct synthesis approach might not always give a PID structure. Sometimes it would give PID, sometimes it would give PI. So because you are only using the model. So see, this is a controller design approach. So again, let me also do this. Then it would be reinforced in your mind. So controller design or tuning generally done with, where is this? Yeah, give me a minute. Somewhere here, I think. Okay, so we can do by looking at the process model, rather including the process model. So now, okay, second is by field experiment. We'll see that. And the third is by frequency analysis. I am saying controller, tuning or design. So these are the and the last at the moment, which when these people did not do things, because these are all classical methods. And the fourth is by means of AI. Of course, we don't learn that, but I am giving you for your information. I have 4 minutes. I'll just give you some hint. Process model based controller design approach would consider the process model in the design analysis. While in the field experiment based controller design method, you would do field experiments. So you currently ignore the model. Why? Because you may have partial information. See, model development is also sometimes you don't have. No, so you are not given with a model. You are only given with a system. Okay, and you have been asked to do the controller design. So you don't have the model. If you have model, of course you can utilize the model. That is double check. But if you are not given with what you have to do, you have to do some field experiments, get some data and do something, look at some profiles, so on and so forth. And the third, of course, we have not learned, and we would learn in the next chapter by means of frequency analysis. How the system react to particular frequency of inputs. And the last is the current hot topic in the area of automation by means of AI. This is technically known as reinforcement learning. You might have heard this term at least. Hope. Is that so? Have anybody not heard of this term reinforcement learning?
Sir, I think it's something related to the AI or machine learning.
Yes, this is proper ML. So what you do is your controller learns by means of interacting with the environment. Typical example is a robot. Let's say a robot walks. You wanted to teach a robot walking. And first step, it might fall down. So you would have to give them a reinforce in his, of course, the artificial brain or in or your neural nets, which is the artificial brain of the what you call robot. Don't take that step, or you have to put leg in a particular fashion. So few times it will fall. Finally, it would become these feedback. So that's why it is called reinforcement. Whenever it does, you would give them a feedback. You keep a step, and it fall down. So what is your feedback? You need to give some instruction. Not correct. Okay. Then he did a good step. He did not fall. You appreciate. Good, reward. So this reward, and so this is called penalty. They say, okay, you are not gonna do. So this reward and penalty would tend to reinforce in its brain, and eventually it become work well. So that is the concept of reinforcement learning, which is of course we are not learning, but I have put things perspective. While 1, 2, 3 we will learn, but there is a fourth dimension which is currently active. Somebody who is interested, read, and it would give you, if you find it to be very, very interesting. I really wanted to do the direct synthesis, but it is 10:59 though. Maybe I'll stop it. I'll continue from here. And the next two classes I would talk about controllers with model base, then you have the field experiments, and I think so on and so on. Yeah, so next 2-3 classes we will wind this up. I hope it is okay, and I think it's also 11. I would don't want to hold you up. Okay, guys, bye.
Hello, sir.
Go ahead.
Just last one. Sir, I was just wondering that what could be an example of giving an input that is not bounded in practical sense.
Oh, it's a very, very good question. So for instance, let's say, okay, so it's practical sense. So that's again, so that's a very good question. Why? Because eventually anything in the physical domain has some boundary. So one typical example is ramp input, unbounded ramp input. This is unbounded, no? But eventually, if you want to implement by a control valve. Control valve will saturate, and which essentially means that it would fully open up, and it cannot open beyond that. So eventually, there are some difficulty to have a fully unbounded input. But anything that has not bounded, for instance, this is an unbounded input with respect to time. But how to implement this to a physical system, that may be very difficult, because many of our physical instruments are working on certain constraints. Is that clarifies you?
Yes, sir.
I think it doesn't seem to satisfy you, but
So maybe in next class. Yeah. Mhm.
okay, not an issue. Okay, guys, bye bye.
Thank you, sir. Bye.